Welcome to Crisis in Perception, where we examine the systems shaping our world one book at a time. Today, we're doing a systems-level analysis of a book that is, I think it's fair to say, one of the most intellectually ambitious books in modern physics.
Absolutely.
It's Sean Carroll's Something Deeply Hidden: Quantum Worlds and the Emergence of Space-Time. And for this deep dive, our sources are focused entirely on Carroll's core argument, which really forces you to confront not just what the universe does, but what it fundamentally is.
Yeah, and that's our mission today, really. We're going to conduct a systems-level analysis of what happens when you take quantum mechanics QM and you take it
Seriously and completely.
right, as a complete description of reality. And this isn't just some philosophical game. Carroll argues this shift is mathematically necessary. It leads you directly and unavoidably to the many worlds theory.
And from there, it challenges our understanding of space and time themselves. Okay, so let's set up the core systemic question right from the start. Quantum mechanics is, without a doubt, the deepest, most comprehensive view of reality we have. I mean, it's behind everything.
Everything. Microchips, lasers, chemistry.
The stability of atoms themselves. It is the most successful physical theory in history. The predictions it makes are just mind-bogglingly precise. And yet, and this is the bizarre part, Carroll points out, a lot of professional physicists will just admit they don't really understand what the theory means.
That's right. It's a very strange situation. They treat the math of QM like he calls it, a mindless robot.
A mindless robot, yeah.
It just performs calculations perfectly, spits out the right numbers every single time, but they've sort of learned to deliberately ignore the radical reality that the mathematics is describing.
So the core question of the book is, what does reality actually look like if we stop treating QM as just a recipe for calculations?
And start treating the wave function as a literal description of objective primary reality. What happens then?
And why is this battle over foundations so important now? Because for decades, the philosophy of physics, it was kind of a sideline issue.
Oh, for sure. It was for retirement seminars, not for serious research.
But we've hit a wall. As we push into the really deep problems in physics, like the search for a quantum theory of gravity, ignoring this foundational mess, this incoherence in the standard approach, is actually crippling us.
Right. The success of the current framework, which is, adequate but conceptually a mess, it blinds us to its own limits. You can't hope to understand things like black holes or the Big Bang or the ultimate fate of the universe.
Problems where you have to merge quantum rules with space-time.
Exactly. You can't do that if you don't first agree on what the quantum rules actually are. So we have to confront it head on, or we're just stuck.
So our approach here is to treat quantum theory as a conceptual system. We're going to look at its structure, its components, the wave function, the Schrödinger equation, and the really radical implications of what Carroll calls the courageous formulation. We're aiming for clarity here, not to perpetuate the mystery that surrounded this topic for, 80 years?
Right. Let's try to demystify it.
Huh.
So to start, we should probably know our guide. Sean Carroll is a highly respected theoretical physicist at Caltech. His specialty is cosmology, gravitation, and crucially for this, the foundations of physics.
And this book, Something Deeply Hidden, is basically his full-throated defense of a quantum-first ontology.
It really is. He's making the argument that the wave function is the totality of reality. It's primary, it's complete, and everything else we see, space, time, particles, it's all derivative. It emerges from that.
To get how radical that is, we have to look back at what it replaced. The original system, the classical system from Newton's Principia Mathematica.
A world of absolute, mechanistic, deterministic certainty.
The clockwork universe.
The clockwork universe. In that system, the state of everything was defined perfectly clearly. The position and the velocity of every single moving part. A planet, a billiard ball, whatever.
And the evolution of that state was governed by these unbreakable deterministic laws. Newton's laws. If you knew the state now, you knew it forever.
Which is where you get that profound thought experiment of Laplace's demon. The idea that if some super intellect knew the exact location and momentum of every atom in the universe right now,
it could predict the entire future and know the entire past.
Exactly. In that view, measurement is transparent. What you see is what there is. Simple.
And then, in the early 20th century, the quantum crisis happens, and that beautiful deterministic clockwork model just shatters.
It really does. Experiments start showing that on the microscopic level, particles are fuzzy, they're smeared out, they act like waves one minute and particles the next.
The fundamental enigma that quantum theory introduces is, I think he puts it simply, what we see when we look at the world seems to be fundamentally different from what actually is.
Yes. And so the classical state position and velocity had to be replaced. And its replacement is the wave function, psi.
Okay, we need to pause on this because this is the central character of the whole story.
Hmm.
The wave function is not a physical thing, like a water wave moving through space.
No, it's an abstract mathematical object. It lives in this incredibly high-dimensional mathematical space called Hilbert space.
And this is where probability enters the picture. The wave function is a mathematical tool that assigns a number, an amplitude, to every possible configuration the system could be in. It's a cloud of potentiality.
Right. And if you want to know the actual probability of finding, say, an electron in a particular spot, you use the Born rule. Probability is the amplitude squared.
So the big conceptual problem, the crisis, comes from the standard textbook rules for how this wave function is supposed to behave, because the rules are kind of schizophrenic.
They are. Part 1 of QM is perfectly clean, it's deterministic. The wave function evolves smoothly and predictably according to the Schrödinger equation. It's as rational as any of Newton's laws.
But then you get part 2, which kicks in whenever you make a measurement. And this part adds these extra, totally unexplained rules that just contradict the smooth evolution of part 1.
Right. When we look at a quantum system, we suddenly get a single definite result. And the textbook says the wave function instantaneously collapses.
Right.
It goes from being smeared out across all possibilities to being locked onto that one observed outcome.
And this collapse is the measurement problem. It's just a mysterious patch. When does a measurement actually happen? Does a bacterium count? A photon detector? How does the system know to suddenly ignore the deterministic Schrödinger equation and switch to this random collapse?
And the textbooks, they're practical guides, so they just gloss over this. But what you end up with is what Carroll calls an oracle.
Right.
The standard text for QM is an oracle. It gives you the right answers for your calculations, but it gives you zero coherent understanding of the underlying physics. We have instructions that work, but we have no idea why the instructions switch back and forth.
And this is exactly why Carroll champions his central thesis, the courageous formulation. He's advocating for the Everett or many worlds formulation, which is built on what he calls austere quantum mechanics, AQM.
And the thesis is, mathematically, very simple. The wave function is everything, and we have to interpret quantum mechanics consistently, which means we remove the arbitrary ad hoc collapse rule entirely.
You just get rid of it.
You get rid of it. You commit fully to the one deterministic rule, the Schrödinger equation, applying everywhere to everything all the time, no exceptions.
And the key takeaway here is if you do that, if you commit to that austerity, the multiple worlds are not some wild speculative thing that Hugh Everett or Sean Carroll added on.
No, not at all. They are an unavoidable, inescapable prediction of the formalism that was already there. It's the purest way to make sense of QM, precisely because it removes the clunky, inconsistent part.
Okay, so let's unpack that. Let's get into the mechanics of how these worlds actually emerge. We're starting with the assumption that the wave function is ontologically real. It's not just information about reality.
It is reality.
And it evolves only according to the smooth, deterministic Schrödinger's equation. Unitary evolution. That's it.
Right. So let's use the classic example, measuring the spin of an electron. Before you measure it, the electron is in a superposition of two states,
Yeah.
spin up and spin down. Its wave function is basically a sum of those two possibilities.
Now, in the old view, the measuring device, a detector screen, say, is outside the system. But in austere quantum mechanics, everything, including the detector and you, the observer, is made of quantum particles.
And so you must also obey the Schrödinger equation.
Right.
So the moment the observer or the detector interacts with that electron, they become entangled. And entanglement is this deep quantum correlation where the state of the detector is now fundamentally linked to the state of the electron. You can't describe one without the other.
So the physical implication is that the observer, just like the particle, now enters a superposition. The whole system, the universal wave function, evolves smoothly into one big, complex state that represents two coexisting, entangled branches.
Exactly. So instead of collapse, you get spreading. The math looks like one branch where the observer saw up and the electron is up, plus another branch where the observer saw down and the electron is down. Both of those possibilities, both parts of that equation, are equally real, and both of those observers are real.
This is what the old Copenhagen interpretation tried to avoid with the Heisenberg cut.
Niels Bohr and the others, they had to arbitrarily divide the world into the quantum system, like the electron, and a classical measuring apparatus. They basically said, the quantum rules apply here, but magically classical rules take over here.
Which is just philosophically unsatisfying and physically arbitrary.
It is. The many-world solution says there is no cut. It's all quantum. And the process that makes these branches look and feel like separate classical realities is called decoherence.
Okay, decoherence. This is arguably the most important physical process in the whole discussion. It's the key. And it is entirely mechanistic. Measurement is simply redefined as any interaction that causes a quantum system to get rapidly entangled with its huge environment. The key words there are rapidly and environment.
So think of it like this. When you measure the electron, you entangle the electron with the detector. But the detector is also entangled with the air molecules touching it, which are entangled with the table, which is entangled with the room, and so on. This entanglement just spreads out at incredible speed into an enormous number of environmental particles.
And this rapid mechanistic interaction doesn't make the other branches disappear, which is what collapse suggests. Instead, it effectively isolates the different components, the branches of the wave, function from each other.
It prevents them from ever interacting again through quantum interference. The information that distinguishes the upworld from the downworld just leaks out irreversibly into the environment.
It's like turning a single pure musical note into just ambient room noise. The energy is all still there, but the coherent relationship is gone. You can't get the note back.
Exactly.
Yeah.
The branches are still part of the same universal wave function, but they're now physically isolated. They appear to be separate, non-communicating classical worlds. And crucially, consciousness has nothing to do with it. This happens whether the observer is a physicist or just a rock getting hit by a radioactive particle.
Which is why many worlds is a consequence, not an add-on. It's the simplest ontology you can get from just the Schrödinger equation.
Right. Every other major interpretation like dynamical collapse theories or Bohmian mechanics, they have to invent complex new mechanisms to get rid of the other branches.
To force a single reality.
Yes. They are literally disappearing worlds theories. MWI is just a coexisting worlds theory that flows from the existing math.
Okay, but this raises the biggest, most immediate question for anyone listening.
Yeah.
If the underlying process is deterministic, the Schrödinger equation is perfect, and all possible outcomes actually happen in separate branches, where does probability come from?
Right.
Why do we use probabilities at all if every outcome happens? And why does it follow the Born rule probability equals amplitude squared?
That's the big puzzle. It's called the measure problem in MWI, and it was a huge sticking point for decades. Carroll's argument here is that probability emerges. It's not fundamental.
It's a higher level concept like temperature or entropy.
Exactly. The concept he focuses on is self-locating uncertainty. So when the wave function branches, the future version of you, the rational agent, you know the universal wave function exists, and you know it contains many copies of you, one in each branch. But you are uncertain about which specific branch you are about to find yourself on.
You literally don't know which copy of yourself you are.
Correct. And in that context, probability stops being an objective physical thing, because it can't be. The physics is deterministic, and it becomes a necessary guide for rational action.
So he uses decision theory to show that for an agent in this branching universe to act rationally, to not make contradictory bets.
Their subjective credences, their degree of belief about being on a specific branch, must be proportional to the weight of that branch.
And the weight of the branch is defined by the amplitude squared, the Born rule.
Precisely. So the rule isn't fundamental to the physics. It's a rule for rational subjective expectation within the deterministic system.
So probability, determinism, and multiple outcomes are reconciled. They just operate at different levels of reality.
Yes. The fundamental level is deterministic and branching. But our experience as observers within an emergent branch is necessarily probabilistic. It's a really brilliant conceptual move.
So if we zoom out to the bigger picture, the question has to be, if many worlds is arguably the most mathematically simple, the most austere interpretation, why was it sidelined for so long? Why did it take decades for the physics community to overcome this conceptual inertia?
Well, we have to map the system of science itself. Look at the actors and the incentives. The actors are the quantum systems, the physicists, the funding agencies, the journal editors.
And the incentives are all over the place. On the one hand, you have incentives like explanatory consistency and mathematical simplicity, which would strongly favor the Everetian view because it gets rid of the messy collapse postulate.
But then you have the most powerful incentive in the whole academic system, empirical adequacy. Does your theory fit the data from experiments?
And here's the paradox that let the inertia just fester.
Since all the major interpretations give the same measurable predictions, at least for now, success in calculation became the only thing that mattered.
Understanding what was really going on was seen as a waste of time.
Exactly. And that entrenched the famous shut up and calculate mentality. It's a perfect example of how success can breed complacency. The incentive structure prioritized measurable, quantifiable results over messy foundational work, and it created a culture where that work was actively discouraged.
So you get these powerful feedback loops of intellectual inertia that actually punish researchers for focusing on this stuff.
Oh, absolutely. Foundational work on the meaning of QM became, and in some places still is, considered barely respectable.
Or even actively disparaged.
Yes. Carroll shares some really powerful anecdotes about this. He says he was once advised to leave his own research on quantum foundations off a major grant proposal.
To seem more serious.
It seemed more serious to the review committee. The work was considered too philosophical, not real physics.
And the story of David Albert is even more jarring. One of the leading philosophers of physics today. He says that after he did his PhD work on the measurement problem, he was basically forced to write a whole separate thesis on more conventional math physics as an explicitly punitive element.
Wow.
Just to get his degree. It was a clear message from the system. Conform or you're out.
And then there's Hans-Dieter Zeh, a pioneer of decoherence, the very mechanism we were just talking about.
The thing that makes it all work.
The thing that makes it all work. His mentor warned him that working on the meaning of the wave function would destroy his academic career. He had a terrible time trying to publish his early, pivotal papers.
And this wasn't just like passive disapproval, it was codified. Carroll points to journal editors like Samuel Goudsmit, who, back in the 70s, explicitly banned papers on quantum foundations unless they offered new experimental predictions.
So the community just collectively decided that understanding how nature really works wasn't the job.
Right. Only making predictions that could advance technology mattered. I love the analogy Carroll uses from the TV show The Wire.
It's perfect for this.
The detectives, they're like the theoretical physicists, meticulously gathering evidence for the big, complex case, the foundational structure of reality. But their bosses, the funding agencies, the department heads,
They have no patience for this incremental frivolity.
they just want drugs on the table.
Right. They want concrete, quantifiable outcomes.
Right.
The next laser, the next microchip, the next headline that gets them more funding for the next press conference. And that structural pressure just pushes the big picture foundational questions aside.
Thankfully, though, the tide has started to turn. We're seeing a return of foundations. And it's not because philosophers finally convinced the physicists.
No, it happened because the technology demanded it. The rise of quantum computing, quantum information science in the 70s and 80s, it forced physicists to take the quantum classical boundary seriously again.
Because if you're trying to build a quantum computer that relies on keeping a superposition stable,
You have to understand exactly what decoherence is and how to stop it.
yeah.
That practical need made decoherence theory essential physics, not just philosophy. The system's needs eventually overcame its own inertia.
Okay, so this is where it gets really ambitious. We're moving from the structure of QM itself to the ultimate frontier, space-time and gravity. If the wave function is everything, what does this radically new quantum-first view say about the fabric of our universe?
Well, it completely flips the script on how we search for a unified theory. The traditional approaches like string theory or loop quantum gravity, they start with Einstein's classical theory of space-time, general relativity, and then they try to quantize it.
They try to apply quantum rules to it.
Yes, but the many worlds advantage, because it's quantum first, it's perfectly set up for a reverse engineering problem. Instead of quantizing gravity, we start with the abstract fundamental universal wave function and the Schrödinger equation, and we work backward.
We have to explain how classical space, fields, and even gravity itself could emerge from that quantum underpinning.
We have to find gravity within quantum mechanics.
But the big idea the book explores is that entanglement underpins the emergence of space-time.
That's the core idea. In this view, locality, the idea that things only interact when they're near each other, is not fundamental. The underlying quantum state is abstract. It lives in Hilbert space. Locality is an emergent feature of our macroscopic branch of the wave function.
So how do you get from entanglement to geometry? That seems like a huge leap.
It is a huge leap. It draws on decades of work, particularly on an information theoretic link. It follows ideas from people like Ted Jacobson, who showed back in the 90s that you can derive Einstein's equations of general relativity, the laws of gravity, entirely from the laws of thermodynamics.
So from entropy and area.
Exactly. Carroll translates this into a purely quantum context. Entanglement is the quantum version of thermal energy, and entanglement entropy is a measure of how much quantum correlation there is between two systems.
And here's the astonishing, crucial postulate.
The area of any region of this emergent space is defined as being proportional to the entanglement entropy between the abstract quantum bits inside and outside that region.
Let me see if I've got this right. The very structure of space itself is built from how entangled its underlying components are.
That's the proposal. And think about the implication. If you define the geometry of space based on entanglement, then that geometry has to obey the dynamical rules of general relativity.
Because changes in entanglement are like changes in entropy.
And gravity is just the thermodynamic-like response of this emergent spacetime to those changes in quantum entanglement.
So you get gravity without having to invent a new particle, like the graviton. It's just what space-time does as entanglement changes.
Exactly. Space and time, which we think of as the stage, are themselves systems that arise from a more fundamental quantum substrate.
But this picture breaks down where gravity gets extreme, like near black holes.
It does. That points to the limits of locality. Stephen Hawking's work showed that black holes have entropy that's proportional not to their volume, but to the area of their event horizon.
Which is really weird for a 3D object.
It's very weird. And it leads directly to the holographic principle. This powerful idea that all the information needed to describe a 3D volume is somehow encoded on its 2D boundary surface.
So our smooth 3D world is kind of an illusion, a projection.
A very convenient low-energy approximation, yes. At a fundamental level, the universe might be better described as information on a boundary.
And what does that mean for the many worlds picture?
It has a profound consequence. If our observable universe has a finite capacity to hold information, a maximum possible entropy, then that means the universal wave function must exist in a finite dimensional Hilbert space.
So not an infinite number of worlds.
No, an enormous but ultimately finite number of worlds. Carroll gives an estimate for the dimensionality of that space. It's 10 to the power of 10 to the power of 122.
Can't even comprehend that number.
It's mind-bogglingly huge, but it's not infinite. And that limit is imposed by gravity.
Wow. Okay, so finally, this whole view, this many worlds view, is crucial for what Carroll calls the reemergence of scientific realism.
Yes, because the standard collapsing interpretation created this dangerous philosophical loophole. It suggested reality wasn't fixed until an observer looked at it, which hinted that consciousness had some special fundamental role.
Right.
But MWI is a quintessentially mechanistic theory. Observers, consciousness, it's all just physical systems that branch along with everything else. This approach defends physicalism, the idea that the world is entirely physical and obeys objective laws.
And it stands in sharp contrast to things like cubism or quantum Bayesianism.
Right, which treat the wave function not as objective reality, but just as a statement about an observer's knowledge. Carroll argues that MWI is vital for maintaining scientific realism, the belief in an objective world, in the face of all this quantum weirdness.
So if we connect all this back to the bigger themes of crisis in perception, what does this whole system of quantum interpretation really teach us about how our frameworks shape what we're willing to accept as reality?
Well, the history of QM is a perfect case study. The standard textbook rules, by making measurement and observers fundamental, created a worldview that was confusing, dualistic, and frankly, unintelligible. It made the world seem spooky or dependent on our minds.
And adopting this austere quantum mechanics, this pure wave function ontology, is a structural correction. It forces scientists to redefine what's fundamentally real, this single, complex, high-dimensional wave function, versus what's emergent.
Right. Particles, space, time, our specific world, it's all emergent. And that requires overcoming centuries of intuition built on classical physics.
It also shows how scientific systems avoid uncomfortable implications. I mean, the rejection of many worlds by so many physicists often just comes down to philosophical distaste.
The incredulous stare.
The incredulous stare, exactly. The idea that an interpretation is rejected just because it's outcome all these other worlds defies our intuition, not because of a scientific flaw. That shows how deep intellectual inertia can run.
The cost of accepting the collapse postulate wasn't a physical one. It was a conceptual one. We traded clarity and elegance for a comforting single reality. And Carroll argues that cost is just too high, especially when we're trying to tackle cosmology.
Let's tie this back to determinism versus probability through the quantum arrow of time. The underlying Schrödinger equation is completely reversible. Physics works just as well backward in time as forward.
But in our emergent world, time flows forward. Worlds branch, but they never fuse back together.
And that irreversibility is the key insight. The quantum arrow of time, the fact that branching only increases, is the exact same physical fact as the entropic arrow of time, the rule that entropy or disorder only increases.
They're the same thing, and both are explained by a profound cosmological fact. The universe started in a state of very low entanglement, very low entropy. It was highly ordered.
So as systems interact, they inevitably get more entangled with their environment. They decohere.
And the wave function branches. This continuous forward branching is entropy increasing. The universe is just exploring more and more of its possible states in Hilbert space.
And we, as observers inside the system, we perceive that exploration as time moving forward and as probabilities unfolding.
Right. So what does this all mean for us?
Yeah, what's the big takeaway?
It means that many worlds helps us see that determinism and probability aren't in conflict. They aren't fighting. They're just describing reality at different levels.
The fundamental level is deterministic.
But our experience within the emergent branching system is necessarily probabilistic.
So Carroll's argument is that the time has come to take the fundamental nature of reality seriously by committing to our most rigorous, consistent physics. And we now have a serious roadmap for how space itself emerges from an abstract quantum state, with geometry fixed by entanglement and dynamics governed by general relativity.
And I think the final provocative reflection for you, the listener, is this. The route to understanding the universe may not be in trying to quantize gravity, but rather in learning how to find gravity naturally emerging within quantum mechanics.
The discussion today was based on the book Something Deeply Hidden: Quantum Worlds and the Emergence of Spacetime by Sean Carroll. We hope this deep dive has convinced you of the profound importance of getting quantum mechanics right once and for all. We encourage you to read this book or borrow it from your local library. This project is free and publicly accessible. If you'd like to support the time, tools, and research behind Crisis in Perception, you can become a supporter on Patreon. For a shorter visual overview of this topic, see the mini explainer linked in the description. If you enjoy this kind of systems-level analysis, please like, subscribe, and comment with books or topics you'd like us to explore next.